Hello guys, this is a new tutorial and in this tutorial we are going to use Plaxis 3D to simulate a raft on sandy soil using Plaxis, and we will see how we can simulate the same thing using my GTS NX, and we will see the difference in the results and compare between them. In this tutorial we will just stop at modeling the Raft using Plaxis, and then in the next tutorial we will use MyDAS, and in the third tutorial we can compare between both results. So here in the Plaxis we will go to start a new project. When we start a new project, there will be a pop-up window. It will ask you to add the title, so we can say Raft project, and you can add the company, file name, and extra. And here in the model he's asking you if you are going to simulate a full model, and this is the element will be 10 nodes element, and the length of 10 nodes, because Plaxis here force you to have one kind of mesh, which is tetrahedral element with nodes at the three edges of the triangular and point at in the middle, as we're gonna see later. And the units here you can change it, but I'm gonna use meter and force for kilonewton, and time will be for day. For the general, we are going using the gravity to be default to 9.8 meter per second square, and gamma water will be 10. We keep the default values. In this tutorial, we are going to simulate a raft foundation with dimension of 20 meters by 20 meters, and the depth of the raft foundation will be 1 meter. And we will put this raft foundation on a section of soil, and this section of soil will be extended from both sides for 2b, which b is minimum length of the raft. Since the minimum width of the raft is 20 meters, so we will extend the domain to 1b from the right and another 1b from the left. We prefer to use one more than 1b because of the distribution of the stresses from Bosenisk and from the bulb of the stresses. So we're gonna extend our domain to be 2b, so it's gonna be 2b or 4 meter from left to 4 meter from the other side. Since our problem it can be considered as asymmetric, so we are going to simulate the corner of the problem, which means we're gonna simulate corner of the raft. So it will be 10 meter by 10 meter. So here we're gonna say that our domain will be 10 meter, which is the problem domain. So if we open the AutoCAD, so it's gonna be 10 meter, which is the size of the raft, and 20 meter is the extension. So our general domain will be 10 meter by 30 meters by 30 meters. To have a better understanding about our problem, we can start to show it on AutoCAD. So if this is our AutoCAD, so I will start to simulate a raft with dimension of 20 meters by 20 meters, and I will extend this for 2b, so I'm gonna say offset 40 meters outside, so this will be my problem. So since this is symmetric, and I will simulate just one corner of this raft or of this problem, so I'm choosing to simulate this corner here. So I will simulate this corner, as we can see here. So The hatched one is the part we gonna simulate, and the dimension will be 40. This is 20 meter in this direction. Let's measure it. It's 40 meters. So we can decrease this to 30 meter. And here to 30 meter by stretching 10 meter, and this will be our problem. In order to do this in Plaxis, we will go to Plaxis here, and we're gonna say our x minimum will be 0, and this domain will be 40 meter, and in y direction it will be the same 40 meter, and I will say okay. So we will start to see our first domain here. So I'm going to go to soil and I will start to create my material. If I checked here, create material, and I went to material type, so creating an interface and soil element, I will choose new, and I will go here and I will choose from the available material here. So if I choose from the available material here, we can see this is the number of the material available on Plaxis 3D, linear elastic, more coulomb, hardening model, soil, and UBC sand. This is can be used for detecting liquefaction, soft soil creep, jointing rocks, and modified came clay, and some other models here. And we can, there is a model here for the concrete. So I'm gonna use for the soil here, I'm gonna model it as sand soil, and I will start to give it unsaturated unit weight as 18 and 19 for the saturated one. Then I will, you can add here the advanced. This is the voids ratio and the damping. This is used for the dynamic analysis, which is out of our scope for now. So I will go to the parameter. I will start to add the stiffness parameter, which is the E, which the E will be like 60 megapascal, which is 60,000 kilonewton per meter square. And for the Poisson ratio, we're gonna add it as 0.3. By default, it will be calculate the G, which is the shear modulus or the odometer barometer. Here we can add the cohesion. So we can add the cohesion. We can't add it 0 because if we added the cohesion to value 0, it will create a numerical problem from dividing over 0, which for the cohesion. So we prefer to add a small value of cohesion, and let's say 0.2 for example. So we can't add it as 0, and we will add 35 degrees for the friction angle since we are using sand. For the dynamic properties, we can add the velocity in both direction, Vs shear wave velocity, and Vb, which is the bulk the compression velocity, and this is important for the dynamic analysis, but it's out of our scope for this model. I will say next. Here we start to classify the soil, and this is very important in the dynamic analysis, but we are not gonna look at this now. We can create an interface element between the soil and the structure element, and we can create a rigid interface, or we can create a manual interface. If we are creating a rigid interface, by default the R, which is the reduction value for the soil properties, which will create which is used to reduce or to create a small element with reduced parameter to simulate the interface between the structure element and the soil. If we kept it rigid, it will, this value, it means there is a rigid interface between the soil and the structure element, it will be 1. And if we make it manual, this will start to be developed to create as an interface between the element. For me, I'm just gonna keep it rigid in this tutorial. So this is for this model, and we'll say okay. We can start to create another material. We can create the raft with different ways. We can create the raft as a plate element, or we can create a volumetric material which is part of the soil with with a concrete parameter to simulate the raft. In this tutorial, I'm gonna simulate the raft as a plate element, and I will add the unit weight of the plate element to be 0 to be equivalent with the weight of the soil beneath it, because I'm going to add the raft at the top. But it's not correct to be at the top because the raft has 1 meter depth. That's why I'm assuming that the unit weight of the soil is equal to the unit weight of the raft, or you can just add the unit weight of the raft here. We can say this is 1 meter depth. So when you add the unit weight of the raft here, you have two ways. Either you just ignore the unit weight of the raft because we're adding it as a plate element, and since we are adding it as a plate element, that means if we add this as a plate element, there will be a substitute from the weight of the soil comparing to the weight of the plate or the concrete, but we are underestimating the weight. But if we want to add another weight here, it can be like if the concrete unit weight is 24 and we add it to 18, that means we can just add like 4 here to substitute, or 5 to substitute for the difference in the weight. But and we can see that it doesn't affect any values here. But once we start to add the stiffness parameter, like the modulus of elasticity, so the modulus of elasticity of the concrete, it's 1.2 E7, and we can see that a lot of parameter will start to be calculated. We have to add the Poisson ratio. We're gonna add the Poisson ratio as 0.2, and we can say okay, we will ignore the relay values A and B here in this model, since we are not talking about dynamic analysis, and we're gonna say okay, and here we just can say raft, and we say okay. We will start to move now from soil to structure, and we can start to simulate our problem. We will go here to create our soil. So we'll create a surface first. So we will go here and we will create a surface. And as we can see here at 0 and 0, and we can start to go to create our raft, and we can say okay. If we just choose this and we want to extrude, we can say that we can extrude our problem here to depth of 60 meter, and we can say apply. So this will be our model for the soil. Then we will go here to choose it, and we start to assign our soil we created here. So the soil we created here, we assign from here, and we start to say this is our soil. No need for this surface right now. Now we can go to create our plate from create structure. So we go here to create plate, and we start here and we create our 10 meter structure element, and this is 10, and this is 10 by 10. This is 10 by 0, and we can say okay. Then we can start to say this is a plate element, and we start to assign this plate element. We can say create plate element from table, and we say raft. Now this is our raft, and this is our soil. Now we can start to assign our load. We will add like 100 kilonewton per meter square load over this. So create surface prescribed load. From here we come and create surface load. So we come here and we create our load, and we say okay. If we looked here in the left hand side, we can see that there is everything we have done in the model. So this is for the soil layer, this is for the geometry, points, line, body curve, surface volume, soil, and this is for the blade parameter. If we open it, we can see that it's assigned to raft, and the soil here, it's as we can see, this is the volume. And if we can see, this is the soil here, and it's assigned to sand. And for the load here, it's assigned to uniform load, and we can start to adjust the load here to be 180 meter load. And as we can see, the total one will be 180. After we finish creating this, we just save our model for future work. And we say save, and then we go to mesh. We'll start to create or generate our mesh. We can create medium or coarse or very coarse or fine. We'll stick with medium, and we say okay. It will start to generate our mesh. We can see here that the mesh size is 0.05, and this is true, and this is the size of the mesh, and create, this is the number of the element, and this is the number of the node. Let's see the shape of the mesh. So we can go here, and we start to see our mesh here. As we can see, this is our mesh. We can refine the mesh in this part as following. We can go here and we choose this, and we choose refine, and we escape, and we choose this, and we come here and we say make it 0.25, and we say please generate this mesh again. So it will start to create the mesh again, and we will start to see, we can see the refinement of the mesh here different than before. Now I can just close, and I can jump to fluid condition. We don't have any fluid. We go to construction stage. In the first stage here, there will be only the soil. Then I can start to create another problem here, or another stage, sorry, and I say this is a raft, or let's call it a structure. And we say okay. And in this case, I will activate the raft, and in the final stage, I will call it load. And in this case, don't forget, and I'm gonna show you something important, but first we will activate the load. But if we open the structure case, we will find that start from the initial state, and the condition of solution is plastic, because we are solving plastic. This is elastoplastic drain or undrained analysis. Consolidation will not be included in this problem because we are talking about sand. If we want to create a consolidation problem, we can just consider consolidation or other models for solution, which we can talk about them in later. Every number here, it means something like the sigma m stage and the weight and other, and and we can like this is referred to the amount of the solution, like how much load did has been solved, as we're gonna see in the answer. But if we looked here at the initial stage, this is initial. For the initial stage, you use the K-node procedures. Here, there are different ways to solve for the initial stage. We have the K-node procedures, or the field analysis, or the gravity loading, or the flow only. Most probably, we are using between K-node procedures and the gravity loading. And the difference between both is the gravity, we use it when we have a sloped surface, or in other cases. However, K-node is very efficient to calculate the lateral stresses, because at the beginning the model start to calculate the vertical stresses, and he uses the K-node, which is in general 1 minus sine phi, using a simple equation to calculate the lateral stresses. When the surface is not horizontal, we have to move to gravity load for, and we can explain why in other tutorial. We will say here okay, and we just start to run our model. He asked if we want to select a points to create graphs. We will ignore this for now, and we will start to solve. As we can see here, he start to solve everything, and sigma m stage, it has to reach 1. So it's 0.4, 0.6, 0.9, and now all the solution, the steps has been solved. Let's go now to check our results. We go now to check the result, to check the stresses and the displacement. We can see here that the maximum displacement from the loading or the third stage is 0.049 millimeter, which is around 4 or 5 centimeters. 5 centimeters is relatively high in the sand soil. That's why we will have to use piles, especially in structures. So our these values, it depend on the code. Let's see our results. We will go to see the total displacement here, or the vertical displacement. We can see here, this is a vertical displacement distribution here, and here we can see stresses, we can see principal effective stresses. Here it doesn't matter the effective stresses and the total stresses, because we didn't include water. For people who doesn't know what is the difference between the total and the effective stresses, the total stresses is equal effective stresses plus water, poor water pressure. The effective stresses is the real stresses in the soil. That's why we are always intrigued to see these values, and the total stresses just account for the weight of the water. But in our problem, we don't account for the water pressure. That's why it doesn't matter. So if we went to principal or total stresses, where there is Cartesian and effective, we can see sigma zz. We can see here, this is the difference between different stages. At the beginning, there is nothing, and this is the distribution of the effective stresses. You can see different results here, the plastic points. You can see here the we can look at the lateral stresses. We can see poor water pressure, but there is no water, plastic point history, and so on. We can see different deformation and stresses and strength. Here we can just look at the, if we choose this one, now we are selecting structures. So if I select this, so now I'm selecting the structure here, and I'm just going here to show the deformation of the structure. And if I want to select here, like go back here, sorry, continue. We can just select structure. and we go here to force, we can show everything. This is a moment diagram. We can see the maximum and the minimum value of the moment. We can see here the distribution. That's why one of the reasons I use it as a blade element, to be able to see the moment and the straining action. So these are different ways. This is contours. So we can see here we'll find the maximum moment at the middle, because in general this will the concentration of the load there will be like at the edges here. It will be more supported, it will push up and at the edges, and it will push down at the middle. So that's why we can find the maximum stresses and the maximum moments at the middle of the raft, since it's rigid. We can see here the total displacement. We can see here you can see the normal and the shear and the moment. So I will stop at this point in this tutorial, and in the next tutorial I will start to add biles to see the difference. As we can see here, we start to add, like, the maximum displacement was almost 5 centimeters. When I start to add piles, I will start to see the difference in the displacement and the effect of the piles. So I will stop at this tutorial at this point and see you in the next tutorial from Plaxis 3D. Thank you guys. See ya.